Hey all dear students, this is Brajesh Chaudhary, your content guru. This video I'm going to take a very challenging problem of electrostatics in which I'll calculate the capacitance of a conducting ring. So obviously when we talk about the capacitance, the material has to be a conductor. So suppose I have a metal ring like this, and what I want to have a uniform charge distribution so that my calculation can be easy. And for that to happen, I will make some assumption. Suppose if I have a ring something like this, so because of the conductor property, isolated conductor, the charge deposits more where the radius of curvature is more. So at the edges, at this edges and on this edge, charge will be more compared to here. So I want the charge distribution to be uniform. So what I want to take, I want to take the thickness or the radius of cross section of this ring to be so small that the charge distribution is uniform everywhere. So this is my ring, conducting ring. Its radius is AR, and the radius of cross section of this ring is small a, and small a is very small compared to the radius of the ring, capital R. And then we have to find the capacitance of this ring. So how we'll proceed? So because it is a conductor, potential would be same everywhere. Suppose what I want to do, the normal process, suppose I give some say charge q to this ring, and then potential of this ring becomes say V, and it is obviously a metal, so potential same at any point. So what I will do, I will find the potential at an arbitrary point, say P. So the potential is V. Then obviously the capacitance will be C is equal to Q by V. But there is a problem here. So what is the problem? Suppose to calculate the potential at point P, I take some element, say here I take some element, say this element, I am going to take this part element is say dq, and this distance is say r. So potential at point P because of this element would be dV is equal to 1 over 4 pi epsilon naught dq by that r. So far so good. And I have to take all this dq from here to here and add the contribution of all the elements to get the total potential at P. So what will happen? If my element is just at P, because there will also be some element, and then from this element the distance of point P would be 0, so that will be not defined. So that is a problem. I will have a point of singularity here. So then the calculation of capacitance will not be possible through this way. And this method also tells you the way we'll proceed, how to proceed this type of scenario. In fact, this kind of integration will become become improper integral. So there is a standard method to tackle such problem is just take a small part from that singularity point, just remove the small part, or take the whole system into two parts. One part would be very small in the vicinity of that part, and the rest other part. So for this part we'll calculate potential separately, and for the other part we'll calculate potential separately, and then add the two parts potential to get the total potential. So here in the next diagram, see, so what I'm going to do, I will divide this whole ring into two parts. This is a part 1 and this is part 2. Part 2 subtends an angle 2 alpha radian at the center, and 2 alpha is very small, so alpha is very small. So basically alpha is very small compared to the whole angle subtended at the center, so compared to 2 pi radian. So, and obviously alpha is very small, so I can also write alpha tending to 0. So this is a very infinitesimally small part 2, and the other part is 1. So purpose of this infinitesimally small part 2 to take to avoid the singularity that will come at P. So what we'll do, we'll find the potential because of the part 1 separately, and potential because of part 2 separately, and then add the contribution of both parts to get total potential, and then get Q by V to get the total capacitance. So let's calculate potential at point P because of the part 1. So for that, let me take this is my reference line, this reference from where I will take angular position. So the positive sense of angle is clockwise, and let me take, this is a little element. Suppose this part, if I give total charge, say small q to the string, this element has a charge dq. The angular position of this element is theta from the reference line, and this dq will obviously be, this charge is uniformly distributed over the whole ring. The whole ring subtends angle 2 pi radian at the center. This element subtends angle 2 pi at the center. So charge dq is simply q divided by 2 pi into d theta. So we'll calculate the contribution of this element potential, and then add all the contributions to get the total potential due to part 1. So potential at P because of due to part 1 for the this element dq, so that potential is say dv1, and this is equal to potential of the point charge formula 1 over 4 pi epsilon naught dq1 divided by the distance of this element to the point P is say r dash. So this is r, and this is r, and this is theta. So using the parallelogram result, we can directly write this r dash is equal to 2r sine theta by 2. So dq divided by r dash, and put the value of dq and r dash. So putting the values of dq and r dash, 1 over 4 pi epsilon naught dq is q divided by 2 pi into d theta, and r dash is 2r sine theta by 2. Now let me rearrange this thing. So that will be q divided by 4 pi square epsilon naught, not 4 pi, 4 into 2, 8 into 2, 16, 16 pi square epsilon naught r, and here that thing will become cosec theta by 2 d theta. This is the contribution due to this element dq because of the whole part 1 will integrate, so that will get v1, so that will be this integration. So as this element goes from here to here, we'll cover the whole part 1. So as we go from here to here, the element of the limit will go from theta will go from alpha to 2 pi minus alpha. So what I want to do, I want to do the short thing. So basically, let me integrate from here to here and just multiply by 2. So what I want to do, I'm taking half of part 1, and because of the symmetry, will double the integral. So this I'm just writing 2 here, and the limit will go from alpha to pi. This is fine. One more thing. Let me multiply this by 2. So if I multiply here by 2, so 2 should come here, and what I want to do, let me write this d of theta by 2, but when I change d theta to d theta by 2, the limits will also change. Earlier the limit was alpha to pi when the variable was theta, now the variable is theta by 2, so the limit will change to alpha by 2 to pi by 2. And now it is straightforward thing, integration. Let's go to the next page. Before going to the next page, this theta by 2 is not looking very good, so it is definite integral. It doesn't matter whether I want to write theta by 2 or y or x. So let me just write in place of theta by 2 to say x. So v1, this 4 by 16, that will become 1 by 4. So Q divided by 4 pi square epsilon naught R cosec x dx alpha by 2 to pi by 2. I am directly writing this integration. This can be done using the by parts, or you can do one thing, that you can just multiply numerator denominator by cosec x plus cot x. So then you can see that the numerator is the negative of the derivative of the denominator, so the integral will become minus ln cosec x plus cot x. So now writing that, so q divided by 4 pi epsilon naught r, minus sign will come, ln cosec x plus cot x from alpha by 2 to pi by 2. So minus q divided by 4 pi epsilon naught square r. So when I put the upper limit, that will become this ln cosec pi by 2 plus cot pi by 2. Cosec pi by 2 is 1, cot pi by 2 is 0, so that will be ln 1, that is 0. So the upper limit will give me 0, and the lower limit will give me ln cosec alpha by 2 plus cot alpha by 2. That needs to be further simplification. So V1 is q divided by 4 pi square epsilon naught r ln cosec alpha by 2 plus cot alpha by 2. Let me break it into sine and cos. So if I break it into sine and cos, that will become 1 plus cos alpha by 2 divided by sine alpha by 2. Now let's break into alpha by 4. So q divided by 4 pi square epsilon naught r ln. So that will become 2 cos square alpha by 4 divided by 2 sine alpha by 4 into cos alpha by 4, and then this will be reduced to q divided by 4 pi square epsilon naught r ln how much, cot alpha by 4. Now we'll do the approximation. So what approximation will do? See, alpha is tending to 0, very small. So if alpha is tending to 0, sine alpha will tend to alpha, and cos alpha will tend to 1. So cot alpha will tend to 1 by alpha. So cot alpha will tend to 4 by alpha. So that will be, so V1 is will become q divided by 4 pi square epsilon naught r ln 4 by alpha, and that is by part potential at P due to part 1. Now let's try to find the potential at P due to part 2. So this is the part 2. This part is part 2. This is very small, alpha tend to 0. So because for this sake of clarity, I have shown that this alpha is large, but this is very infinitesimally small. So this small part can be thought of kind of a this cylinder like this. This is a very enlarged part of this. So this radius is r, so this length is r alpha, so this length is r alpha, and this length is r alpha, and this is like a cylinder, and radius of the section of this ring is small m. And now just recall that this ring is a solid ring. It can be hollow also. So suppose ring is solid, but this is a conducting ring, so the all charge will be at the surface. So the ring is only at the surface, not on the interior of the material of that ring. So now what will make, I will make the elements. Because of this part 2, we have to find the potential at P. So let's go to the next page. This is the enlarged part of the part 2, and suppose I take an element here. So this is at a distance x from here. I told that all the charge that we give to a conductor at right side the outer surface, so the element that will take will not be kind of a disk. It will be disk, but the charge will be on the surface, so effectively that will like a ring. So I have taken an element in the shape of a ring whose radius is a and thickness is dx. So this ring has a at a distance x and this radius is a. So all points of the periphery of this ring at the same distance is small r. So if I talk about the charge of this ring, suppose the charge of this ring is dq. So this dq will be, this total length of the ring is 2 pi r and the length of this element is dx. So this would be q divided by 2 pi r into dx. Now because of this element, because this is a ring and this point P is the axial position of the ring, all the points are at the same distance. So and this r is obviously square root of x square plus a square. So potential at P because of the part 2, this element dq dv2 is equal to 1 over 4 pi epsilon naught and the dq divided by that r. So put the value of this dq and r, so we'll have this is a 2 pi r, multiply this by 2 pi r, so that will become 8 pi square epsilon naught r and q, write q here, dx and divide by x square plus a square. Again this is standard integral. So now because of this whole part, the potential at P V2 will be the integration. This integration, the limit of x will go from this is a positive x, so minus r alpha to plus r alpha. So again I will do the half integration and double that integral. So let me take this integration from 0 to this r alpha and just multiply it by 2. So this integration will give me q divided by 4 pi square epsilon naught r, and this integration is basically ln x plus square root of x square plus a square, and then put the limits 0 to r alpha. Go to the next page. So v2 is equal to q divided by 4 pi square epsilon naught r ln x plus square root of x square plus a square, and this x goes from 0 to r alpha. So putting the limits, q divided by 4 pi square epsilon naught r, the upper limit will become r alpha plus square root of r alpha square plus a square minus ln x square. In place of x square I'll put 0, that will become simply ln. And here we'll take this approximation. This a is very small. This a is very small. We have chosen, in fact a is so small, that was our compulsion to make the charge distribution uniform. So a is very small. So this r alpha can be neglected in comparison to, sorry, a can be neglected in comparison to r alpha. So this part will become ln 2 r alpha, and this is ln a. So finally we will have this v2 is equal to q divided by 4 pi square epsilon naught r ln, this is a 2r alpha, ln 2r alpha minus ln a, so that will be ln 2r alpha by a. That is my equation. So we got the potential at P due to both parts. So total potential at P because of part 1 and part 2, that is a V is equal to V1 plus V2. And both the thing q divided by 4 pi square epsilon naught r was common. So because of the part 1, potential was this into ln 4 by alpha, and because of part 2 at point P, potential just calculated q upon 4 pi square epsilon naught r into ln this ln 2r alpha by a. So ln 2r alpha by a. So that will become q divided by 4 pi square epsilon naught r ln a plus ln b is ln a into ln b. So if I multiply that thing, so you can see one good thing, that this alpha was a kind of a intermediate thing. So obviously in the ultimate answer there should not be anything alpha. Alpha was my choice, and that is now going away. So if I multiply that, this alpha and that alpha will cancel. So finally we'll have a 8r divide by, so we got the potential at point P, and this point is an arbitrary point. So in fact this is the potential at any point of this ring. Now the capacitance of this ring. So we given a charge q here, so capacitance and the potential becomes v. So capacitance is equal to q by v. Got this v, q upon 4 pi square epsilon naught, and this ln 8r by a. So the capacitance of this charged ring become 4 pi square epsilon naught r divided by ln 8r by a. So that is the capacitance of this ring, and there is a purpose of me to take this problem, because my next video is going to be IIT-JEE problem 2021. In that problem there was an electrostatic lens. It is a very lengthy question. If I make the solution of the problem, it will go very long. So I will, this result I'll use there, and using this result I'll do the other parts. So enjoy this video. This is indeed a very good problem, and this is indeed a very good technique to avoid the singularity points. Thank you for watching. Enjoy.